All right, so basically on this short course, what we're going to do is give you an introduction into a series circuit, and hopefully we'll have a better understanding how to put this on our breadboard. So first of all, we want to do is look at what a series circuit is. Before we actually get into the guts of the series circuit, we need to identify symbols. First of all, we have a DC battery. It has a positive rail, has a negative rail down here. So this is a negative. The negative is always a shorter horizontal line. The positive is always a larger horizontal line. So in our case, we actually do conventional current flow. Conventional is from positive to negative, and electron flow is negative to positive. This is actually discussed in your book, so please pay attention to that. We also know that we have some resistors here, R1, R2, and R3. Retrospectively, R3 is our resistors, and they can represent anything. They can represent any physical real-world item. For example, it could be a hairdryer, it could be a computer, whatever it is, it's a load. That's what a resistor is, a load. If we look at the series circuit, we know that we have three resistors, R1, R2, and R3, and they're connected in series. How do I know that? Well, we take a look at this. Here's line, here's point A. Point A is everything on this line. So if we look at point A right here and hits this resistor, well, it's going to slow down. Those electrons are going to slow down. So when it slows down, it gets back to B. Well, it speeds back up. And then it hits R2. Well, it slows back down again, and it continues on through C, speeds back up, goes over to D, and then returns. Well, we know that. From that, we can actually make a conclusion that a series circuit, the resistors are additive. Basically, the resistance is additive in a circuit, so that they're added together, they're connected to each other in a circle, if you want to look at it that way. Basically, in a circle. So if we look at that, if we have that information down, and we know that we have voltage, current, and resistance, and from Ohm's law, I is equal to V over R, we can actually come up with quite a bit of information on this circuit here. For example, R total is equal to R1 plus R2 plus R3, which if we do this right, R1 plus R2 and R3, well, if we do 100 ohms, 100, I'm not going to put the symbols in, the symbol in it, because it is hard to do on this using multisim, and we come up with is equal to 900 ohms, and that's the omega symbol. So that's our total. Well, now we want to do is find I total. Well, I total is the same throughout the circuit. So if I actually take a amp meter right here and I put it into the circuit here, and I delete that, and I copy, Control C, Control V. I want to show you and prove to you later on here that current is the same for the circuit. This is in series. So an amp meter must be connected in series in a circuit. Basically, you break the circuit where you want it. You connect up one lead to one side of your point and the other lead to the other side. So basically, you're making a hole, and then you're patching the hole with the multimeter. So that's how you do amps. And we want to do is set these for amps, because if we don't, we will have a problem. So we're going to do is set these for amps, and they are set for amps. So we have R1, R2, R3, so R total. So now we're going to find I total. Well, I total is just equal to, using Ohm's law circle, I is equal to the voltage and the resistance, divisible into the resistance. So I is equal to V over R, or R, you're getting some sort of current. Current is the rate at which electrons are flowing. So we have a 12-volt battery, and we divide that by our total. Well, that R, it has to be R total, so let's get that in there. Our total is equal to 900 ohms. 12 divided to 900 gives us 13.33 milliamps. 13.33 milliamps. You notice I'm using the metric prefixes. Milli is really small, so it's 10 to the minus 3. It's 1,000. So now what we have left here to do is actually find our voltage total, our voltage drops, So we can find VR1, we can find VR2, and VR3. Well, when we want to find voltage drops, what we are physically doing is taking this multimeter. So I'm going to take another multimeter here, Control C, Control V, and we're putting it in parallel. While this guy was in series, for current, voltage is in parallel. So if we look at it, that is parallel. So if you are making your circuit up, you want to put it so it is in parallel to the circuit. So it's going across it. Again, I'm going to set my meters here up for voltage, and I do have flat line for battery for DC. Now I can do all these. Control C, Control V. I'm just copying and putting my meters in, and Control V. I'm going to keep everything. Now this one I'm going to flip horizontally, because what happens is if I didn't, you get a negative. You get a really you get a negative value, and you're really asking me, why is that a negative value? Well, the meter's put in backwards. So if we want to find the voltage drop across these resistors, well, what we're doing is how much voltage is actually being dropped based on the current and the resistance. So voltage, based on Ohm's law, is equal to V is equal to I total times it by, in this case, R1. So if we do that, because why am I using R1? Because I want to find the voltage across R1. So in this case, I have I total is 13.33 milliamps. Times that by 100 ohms. And that gives me approximately 1.3 volts, 1.33 volts. And if you're not sure, you take that and you multiply your current, and it's 1.33 volts. Okay, so now we take it by IR2. Same equation, but different resistors, I total. I'm going to put IT for that, just for the giggles of it. Times it by R2, because I'm using R2 now. So that gives me 13.333 milliamps. Times that by 330 ohms. Well, it's going to be approximately about 3.3 higher than the other one. So it should be gives me approximately about 4.99 volts. So if I actually do that, so if I actually take times it by 330. 4.4, I was right, 4.4 volts. And finally, VR3, I'm going to bring this guy back up a little bit here. VR3. And I'm just going to put myself back. I can see myself. So VR3 is going to be equal to I total times it by, in this case, 470 ohms, which is going to give us 13.33 milliamps times it by 470 ohms. And yep, that looks good. That should be equal, not there. There we go. I'm going to actually, I messed up on this. You just didn't catch that. I was wondering why my numbers were off here a little bit. Trying to talk and do things at the same time. You're not working. Okay, 13.7. There we go. So all we have left is, so 13.33 e to the minus 3 times it by 470 ohms. I get 13.333 e to the minus 3 times it by 470 ohms. There we go, 6.26. 6.26 volts. So, as you can see, from what we have on the circuit, I'm just putting myself up here a little bit so you can actually see what's going on here. I'm going to close out some stuff. I'm just moving things around a little bit here. All right. Ooh, that was not good. Okay. You can tell I'm an amateur at this, so you're just going to have to pay attention and hopefully give me some little slack on it. So, cutting across. There we go. So we have our stuff, which is really good because we needed it. And right now, what we have is our voltage drops and our current. So now what we can do, there's a second way actually to find the voltage drops across VR1, VR2, and VR3, and that's called the voltage divider rule. Voltage divider rule. Basically, the voltage divider rule says that you take your Rx and divide it by RT, which is your basically Rx is like R1, R2, R3, divided by R total. And then what you do is you multiply that whole thing times that by V total. And what you're doing is that's a ratio, Rx over RT. Looks like I'm running out of time, but you get that, and pretty much. So we can get into the breadboard section of it. Hopefully we'll get into, I'll go a little more deeper, but I'm going to pause this for now, and we're going to stop this and continue on in a second.